Okay, so today I'm going to go over quick question 70 as well as unit 4.5 using graphs to estimate values. And we'll start with the quick question sheet. First one we have here is fill in the missing values. So here on this top line we have a set of coordinates and you can see the x value right here. The first one is going up by 1 each time. So we're going from 0 to 1. 1 to 2, 3. So that's going up by 1s, and this is jumping up in our second coordinate here. That's going up by 12, 12. So this next one here is going to go up by 12 again, so that has to be 36. Now when we look at this bottom one here, we can see in the bottom that we're starting at -4 in the x, and it's moving to -2, so that went up by a +2. Then to 0, which would also be +2. And then 2. So if we're adding 2 each time, this would make 2 plus 2 would be 4. So 4 would go there. And now to find the other missing value, we're going to work backwards with our y value. So this starts at 18 and it's going down by 8. Then it goes down by 8 again, down by 8 again. So if I'm at -6 and I have to take 8 away one more time, -6 take away 8 is a -14. So those are the coordinates we have right there. Next, we'll come over to the graph, and it says, why is this graph misleading? And it's misleading because when you look at it, the first side has 77.3 miles per hour. That's how fast the knuckleball is. And here we have 75.3 miles per hour in 2013. And if you didn't know better, it would look like this is like half, maybe even less than half, because when you draw a straight line going straight across, you can see that this one here is only about half of this one over here. But 77.3 is not half of 75.3 is not half of 77.3. What it should look like is you should have a graph that looks like this. So you'd have one bar. You'd have one bar that would go like this, 77.3. Then you'd have another bar that would go like this, 75.3. So that way you don't have one bar that looks like it's half the size of the other bar. They look like they're very similar, but just one is slightly shorter. This one is indeed smaller, it's just not half as small as that. That's why this graph is misleading. Next, we'll move down to the sale price of a camera. So here, we have a sale price of a camera, and it's telling us that the sale price is $280. The sale price of a camera is $280. If the sale was 20%, what was the original price of the camera? Okay, so if we can think about this in a whole bunch of different ways, but let's just think about this in terms of a number line. So I can bring in a number line right here. Let's say this here is 0%, and this is 100% of the price. And we know that if we break this up, if we say that this is, we know that if we take 20% off, so we'll say this is 20% right here. So if we say this here is 20% off, because think of it this way, if you have $280 $280, and we know that that is the price when it's 20% off, then that means $280 must be 80% of the real price. So if this is 80% right here, we know that this is $280. So the question becomes, how much is this 20% worth, so that we can find out what the original price was? So I can think of it this way. I know that this is 80%, and that's 280. So this means that I have 1, 2, 3, 4 parts of this fraction, this number line, make up 80%. So if I take 80%, if I take 280 and I divide that by 4, that is going to give me 70. So I know each of these must be, this must be $70, $140. Then this one here would be $210. And each time I'm going up by 70. I go up by 70 again here to get to my 280. So if I want to know what 100% of my price is, I have to take my $280 and add 70 to it, which gives me $350. So the original price was $350. Now, the last question here, evaluate -5 plus -5 divided by -5. And really what we need to rely on here is our order of operations. And the question is, do we do the addition or the division first? And if we follow our order of operations, what we would do is we would do this division first. So I would work out -5 divided by -5, and what that would leave me with is I'm going to have this -5 from here plus -5 divided by -5 equals 1. Because any number divided by itself would equal 1. So I'm left with -5 plus 1. -5 plus 1 equals -4. So the answer to this question is -4. Okay, so that's quick question sheet 70. I hope that all made sense. And if you have any questions, please let me know, and I can go over them again. Now moving on to using graphs to estimate values. So this is unit 4.5. This is the last section of unit 4. And we'll start with this here. It says a city has grown over the past few years. The table and graph shows how the volume of water used each month is related to the population. So here we have a table of values that has the population, so how many people live in the city each year, and how much water is used every month. And this is measured in megaliters, ML, which stands for megaliters, and a megaliter has 1 million liters in it. So when you look at this 750, you can also picture that as 750 million liters. And you can do the same for all of these here, just so you have an idea of what this really looks like. So this here would be 1.35 billion liters, 1.65 billion liters. But because we want to put it on a graph, we want to use a measurement that's more friendly using these smaller numbers like 750, 975, 1350, 1650. So we measured it in megaliters, which has 1 million liters each in it. So 750 megaliters, and that's what we have measured on our graph over here on our y-axis. So remember, this here is our y-axis, this is our x-axis, this is our x variable, and this is our y variable. And we took our table of values and we made a graph. So 100 and 750 makes this point, and then we plot all 4 points right there, and they form a line. And it asks us to estimate the monthly water usage for a population of 150,000 people. So notice they skipped from 130,000 to 180,000. So if there was a smaller town that wanted to know how much water they're going to need when they get to 150,000 people, they could look at this graph and estimate. So first thing we want to do is find 150,000 on our population. And there's 100,000 and 200,000. So 150,000 has to be right in the middle, right here. So mark that point off here. This is 150,000 right here. Oh, no, not quite actually. 150,000 should be right in the middle there of those two lines. So there's 150. I'll just mark it as 150 right here, just so we know. And if I want to figure out, now that I know where the 150 is on my population, I want to figure out how much water usage over in this column I'm going to need. So what I can do is I can draw a line straight up to my line here. Once I intersect the red line, I can then go horizontally straight across right to here, and we can see that that is going to be a little bit above 1,000. Not quite so. I know that this point right here is 1,250 megaliters. So this would not be anywhere near that. So this might be a good estimate for this one here would be 1,100 megaliters. So now for the next part, estimate the population when the monthly usage is 1,400 milliliters. So we can tell that 1,400 milliliters would be just under where the 1,500 milliliter mark is. So maybe right about here. We'll say that is 1,400 right there. We do the same thing, but in reverse. Now we go and draw a horizontal line this way till we get to our line. And we can come straight down now and see where we end up. And we can see that we end up right here, just a little bit below 200,000. So you might want to estimate something along the lines of 190,000 liters. Oh, sorry, 190,000 people. And then finally, it asks us to predict the water usage for 250,000 people. So if we look at this here, we can clearly see that there is nobody, or the graph does not go to 250,000. So if I scroll down, oh, all those figures are leaving with me. There we go. One moment. So, actually, I guess they don't show. So what I'm going to have to do here is I'm going to have to extend this graph. So that's 200. I got to extend my line this way, and I'm going to have to also extend it up this way. So I can see that if I want to go to about 250, that's going to be 1, 2.5 lines. So 1, 2.5 lines. So that's where my 250 is going to be, is right about here. This here would be 250,000 people. And now if I continue and I extend this line straight out like this, I can come up like this to where I intersect this line right here, come straight across to right about here. And now looking at the measurements that I have here, for every 2 lines I go up about 500. So this here at the very, very top would be 2,000. And that's just under that. So I would say this here might be 1950. So I might want to say 1950 megaliters. That would be a good estimate on that one there. Now, again, we're just estimating at this point, but that would be what I would believe would be a good estimate. Okay, so, So now we'll come down to this connect section and we'll look at this and we'll discuss what we're actually doing, what this is called. So this graph shows the distance traveled by a car on a highway changes over a 4-hour period. To draw the graph, we plotted the distance traveled every hour and then drew a line through the points. We can interpolate to estimate values that lie between two data points on the graph. And that's exactly what interpolate means. Interpolate is the definition is to estimate a value that lies between 2 points on a graph. So that means we can interpolate, means look inside of this graph in order to get the data we're looking for. And in this case here, what it's telling us to do is it's saying to estimate the distance traveled in 1.5 hours, begin at the 1.5 mark on the time axis. So as they show us down here, this is where 1.5 hours is. And on this chart here, the graph is the same as the graph up top here. And all they did was they put the 1.5 hour mark right here on the graph. Then they go up to where it meets the line right here. And they come straight across to here to figure out, to get an estimate of the value of how far they traveled after 1.5 hours. And you can see that it is a little over 100, but not quite to 150. And they say here that it is about 120 kilometers an hour. So that's a good estimate, 120. Now, the next thing it says, is they want to estimate the time it takes to travel 300 kilometers an hour. So, 300 kilometers. So if they were to travel 300 kilometers, which would be right here, 300 kilometers, we can mark that on our graph right here. This comes straight across till we hit the red line. And then we come straight down. And we can see it's over 4.5. But not quite 4 hours. So you might want to say 4 hours and 50 minutes, 4 hours and 45 minutes, something like that. And when we go and we look down a little further, oh, those lines are moving on us. There we go. That's close enough. So when we go and we look down here, we can see that it was indeed 3 hours and 45 minutes. All right. So next, we're going to continue to think about a car traveling. And it asks us, it says, suppose the car maintains the same average speed. We can extend the graph to predict how far the car will travel in a given time or predict the time it takes to travel a given distance. So what this means is that even if, as it showed up in the graph here, we only have how far the car traveled in 4 hours. And let's say that's all the data we have. Well, we can then extrapolate. This is called extrapolation when we use a graph to predict. So we don't have the information, so we're going to predict in this way. We assume the relation is linear and we can continue, it continues to be linear. We can rule to extend the graph. We can use a ruler to extend the graph. So basically, when we extend our graph beyond the data and then we make a prediction, this is called extrapolation. So extrapolation is to estimate a value that lies beyond the data points on your graph. So this is going beyond the data we have. We don't know this data, but we make the assumption that it continues to be a linear relation and he stays traveling at the same rate of speed. So if the car does remain at a linear speed, it wants us to estimate the time it takes to travel 450 kilometers. So what they've done here is they've extended the time axis an extra 2 hours to 6 hours, and the distance axis another 200 kilometers to 500. And they start here at 450 kilometers and go across till we hit our red line, and then back down, and we can estimate that it's going to be just a little over 5.5 hours. So it's saying 5 hours and 40 minutes is how long it would take. So we extrapolate it based on the fact we know how far the car has traveled in 4 hours. So we predict how long it's going to take us to travel this distance, and it would be 5 hours and 40 minutes. Example number 1, use interpolation to solve problems. Jenna borrows money from her parents for a school trip. She repays the loan by making regular weekly payments. The graph shows how much or how the money is repaid over time. The data are discrete because payments are made every week. So that means you wouldn't join them with a line. They're each individual, they're discrete data packets that don't get joined with a line. The reason that these look like they're joined with a line is not that they're joined with a line, they're just placing a ruler over the points to show that it forms a straight line. And we're asked, how much money did Jenna originally borrow? And we can tell that by going right here at the zero on the time axis, which is our x-axis. So remember, this here is our x-axis, this is our y-axis. It's always this way. We call this the time axis because it represents time, and this the money axis because it represents the money. So on the time, when the time is 0, she had $200. So we know that right there, this $200. So she originally borrowed $200. How much money does she still owe after 3 weeks? So what we will do now is look at where the 3-week mark is here on our graph, which is right here. We will draw a line straight up till we hit this ruler, which is representing a line. We don't join the points with the line, but we can use a ruler, come straight across to here, and we can see that this would be $140. So she owes, after 3 weeks, $140. Finally, it asks, how many weeks will it take Jenna to repay 1/2 of the money she borrowed? So if she borrowed $200, we know that half of 200 is 100, and that would be right here. So this is where $100 is. So we can take that point there of $100 and come straight across till we hit here, and then straight down, and we can see that it would be 5 weeks. That's how many weeks it would take her to pay back half of the loan. Okay, so is there any questions? No? Great. All right, so moving on to this next section down here. Solutions, or a solution. Now, so this is the solution from what we just went over. And you can see that it was 200. It was 200 she started with. We can see that by going up where 0 is, that it is 160, between 120 and 160, so it would be 140 after 3 weeks, and it would be 5 weeks. So next we're talking about extrapolation. Use extrapolation to solve problems. Remember, extrapolation is when we need to look beyond our graph. So this is saying to us, we have Maya jogs on a running track. This graph shows how far she jogs in 10 minutes. Assume Maya continues to jog at the same average speed. So this is very similar to the car, only Maya here is running or jogging, and she's staying at the same constant speed. Predict how long it will take Maya to jog 2,000 meters. So as you can see, this doesn't go to 2,000, so we'll have to extend that. And then this is asking us predict how far Maya will jog in 14 minutes, and this only goes to 10, so this will have to be extended. And what assumptions did you make? So let's go down, because they have the graph extended down here below, and you can see they extended our time axis right here from 10 minutes to 18 minutes so we could be able to answer all the questions properly. And they extended our distance axis from, I believe it was 1200 all the way up to 2000. So the first question asked us to predict how long it will take Maya to jog 2,000 meters. So the first thing we do is we come down here to where 2,000 meters is, and we go straight across till we hit our red line, and then we come straight down, and we can see it's a little bit above 16, but just a little bit below 17. So if we're just estimating, we could say almost 17 minutes. Next, it asked us to predict how far Maya will jog in 14 minutes. So that's why we also needed to extend the time axis. So we could come across to 14 minutes and go straight up till we hit our red line and straight across. And we can see that this would be right in between 16 and 18. So this would be 1700 right here. And this here is 17 minutes right there. So 1700 meters. So just a little bit under 1700 meters. So when we're estimating, we can say it is between 16 and 17 minutes to jog 2,000 meters, closer to 17 minutes, but still between 16 and 17 minutes. And at the beginning at 14 on the time axis, we move across, we can see the distance is about 17 meters in 14 minutes. So in 14 minutes, Maya will jog about 1700 meters, which is what we had up here. Okay, oh, my 1700 seems we'll get that back in place. Okay, so now the last question is, what assumptions do we need to make? I assume that Maya will continue to jog at the same average speed as before. If Maya was to run faster or to run slower, then this is no longer a linear relation, and then none of this will work. So now number 3, oh, look at that, 17. That 17 is going somewhere too. Let's get that in place. Okay, so example 3, and this is the last example. Interpolate and extrapolate to determine the values of variables from a graph. So this is giving us equations, and then we need to determine what the answer is going to be based on looking at the graph. And first it says determine the value of x when y is 3. And in order to do that, if I was to label this graph here as 3 on the y-axis being right here, so that's 3 labeled on the y-axis right there. As you see, as I go across, I don't come into a red line because this would require extrapolation. So this is beyond the graph. B asks us, determine the value of y when x is 5. Well, x would be 5 right here. So now that I know where x is equal to 5 at, I can then use that to determine the value of y when x is 5. So from this point here where y is 5, or x is 5, I can come straight up till I hit my red line, straight across to here, and I'm a little bit below 7, so I'm going to estimate that to be about 6.75-ish. No, yeah, something along those lines. It's about that. But now in order for me to be able to answer the first part, I need to use extrapolation, and in that case I can look at the graph down here that has been extended. And I can see right here where y is equal to 3, that if I follow this blue line across to where it hits the red line, which was extended, I come down to -6. So I can tell for sure that the answer to part A is -6, because that is where we end up. Okay, so that is it for this example. And now finally, we go on to questions 1, 2, and 3. Actually, no, I'm going to cover these questions 1 through 10, in the next video. So if you have any questions about this video or what we covered in section 4.5, using graphs to to estimate values, please send me an email, and I hope this video was helpful. Thank you.